So now we want to start looking at some integration techniques. So if you remember with derivatives, we had a lot of different techniques to take the derivative, right? We had like the power rule, the product rule, the quotient rule, the chain rule. So now we want to look at some of those equivalent techniques in integration. And what we're going to find is that in general, integration can be quite a bit trickier than differentiation. It shouldn't be too surprising. Like typically, we look at the easier one first, and then we look at the inverse of that, which is a little bit trickier. Like we looked at exponents, but then we looked at logarithms, and logarithms are a little bit trickier than exponents, right? Even something as simple as like addition and subtraction. Typically, subtraction is a little bit trickier than addition, right? So hopefully it's not too surprising that integration is a little bit trickier. And in general, what we're going to find is that there are some things that we just, we really can't take the integral of, right? We can't actually integrate them. So even with all these techniques that we're going to look at, there are still some things that are kind of outside of our reach of doing them by hand. And we don't really run into that problem with derivatives. We can pretty much take the derivative of anything, assuming it is differentiable. So it's kind of an interesting case. So I just wrote down a couple of different integrals here. So you can see like when you have something like 1 over x squared, as we saw, right, this is just a simple power rule, and it's analogous to the power rule in differentiation. And then we just end up with negative 1 over x plus c. But then doing something as simple as just changing the denominator to x squared plus 1 drastically changes the integral, right? Then we end up with arctangent. And I think I mentioned in another video. And, we're not really going over too much trig here, but this is kind of an important one to know because this is kind of a form that does come up every so often. But then changing it to something like x squared plus x, now it's completely different and we need a completely different technique. And you wouldn't think maybe that such a simple change would change it so much. If we made this simple change in differentiation, it really wouldn't pose too much of a problem to us. But here, it actually does. So the first technique that we're going to look at is called substitution. So this is kind of, this is analogous to the chain rule for differentiation. So it kind of will undo those derivatives we would have found by doing the chain rule. Now we're working backwards, to get back to the original thing we took the derivative of. So this substitution will allow us to do that. So let's start by looking at an example here. So let's try to find the integral, and we'll just do the indefinite integral versions of these. Of x squared minus 3 to the third times 2x dx. Okay. So, if you were just going about trying to do this, what you would probably want to do is you'd probably want to multiply that out. But of course, that's going to get really ugly really fast, right? You're going to end up with like x to the 7th power at the end of it. And that's fine. Like you can do that. You can do the algebra and get there. But there's an easier way to do it. And that's using this thing called substitution. So we've kind of seen this concept before in other algebra things where we made a substitution, meaning that we used like kind of a dummy variable in as a substitution in the problem just to make the problem a little bit easier. So we can do that here too. We typically use u as the substitution variable, and for that reason it's often called u substitution. So I guess I can write that right there, but you can use any variable, of course. So what we want to do here is we want to let u be equal to kind of like the main part of the integral usually. But you might have to kind of play around with it and see exactly what you want u to be equal to. So like here, if we let it be equal to the x squared minus 3 part, for example, then the advantage of this is that this term right here is just going to be u cubed, which is a lot easier to work with. Then we don't have to worry about multiplying it out, right? We don't have to worry about having a binomial and having to do all that multiplication with the distributive property or the foiling or whatever. The difference with this substitution in this context versus other context is namely going to come from that dx term. So up to this point, this has really just been there to kind of indicate what the variable is. But we want to remember exactly what dx stands for, right? Dx is an infinitesimal, meaning an infinitely small quantity, basically. Infinitely small as in approaching zero quantity, not negative numbers, right? So if we think back to like estimating the area under a curve using rectangles, right? This dx, this represents the width of those rectangles. But this is where that fractional derivative notation kind of comes into play for, I really believe the first time. I guess it kind of came into play with the chain rule, so I guess maybe it's not surprising it comes in here too, because this is like the chain rule. But if we look at du dx, okay, and we're doing this because, you know, this, if we make a substitution for x, then it kind of follows that we should be making a substitution for dx, even though we've been kind of ignoring that. There's some physical meaning there, so we need to also substitute that part too. So to do that, let's think about du over dx. So this is the derivative of u with respect to x. So this is just going to be 2x in this case. And look, that's this term appearing right here. And that's not by accident. That's what we want here. Now, this right here is another reason why we kind of use this fraction notation, is because in this context, this is another context where it behaves like a fraction. We can multiply both sides by dx, okay, to kind of cancel out here. And you get, you end up with this kind of expression, okay? That's kind of like the intuitive way of thinking about it. We're not really like multiplying it. We're kind of just, we're doing what we call separating them. There's if you ever like look at differential equations, there's a category of differential equations called separable differentiable equations. And this is kind of what you're doing there as well. So we're kind of separating the two variable parts with their respective variables. So we're separating the du part onto the u side and the dx part onto the x side. So what we're left with here is an expression for du, which is equal to 2x dx. And that's very convenient for us because that's telling us that this whole part right here is equal to du. Okay. So when we go ahead and make the substitution, we're going to end up with u cubed du. And now that's a lot easier to integrate, right? We don't have to worry about any kind of, you know, multiplication or binomials or foiling or anything like that. It basically skips all of the algebra, you know, with a little bit of calculus. So when we go ahead and do this now, this is just a straightforward power rule, right? U to the fourth over 4 plus c. And of course, we still want our answer to be in terms of x, so we can go ahead and sub it back in. So this is going to be x squared minus 3 to the fourth over 4 plus c. And then that'll be our final answer. So you can confirm that this is true just by taking the derivative of this. So if we go ahead and do that, so I'll just do it in red right here. So we get 4 times x squared minus 3 over 4, and then times 2x via the chain rule. And then the derivative of the constant, of course, is 0. So these cancel out. So we have x squared minus 3. Sorry, I forgot the 3 up here for the power rule. Times 2x. So we end up getting what we would expect. So we can see that it does work. Okay. So this kind of opens up a whole new class of functions that we can integrate. Okay. So essentially we're trying to look for letting u be equal to some part of it where the derivative of that part is equal to some other part. Okay. And of course it won't always be possible. This isn't like a catch-all. We can do any integral with this, right? There's still some other techniques we'll look at, but this definitely opens up a lot more of them. So let's look at another example here. And of course, we shouldn't always expect it to be set up as nicely as the last one, where the derivative of that expression is exactly the other part. Sometimes it'll be kind of close to it at least. So let's look at the integral of z times the square root of z squared minus 5 dz. So the kind of the main part of this integral is the z squared minus 5 part. And I say the main part, it's really, you know, kind of subjective. So maybe it's not really good to think of it in terms of like the main part necessarily, but just the part where you can kind of see that if you take the derivative of this, you're going to get something like just z, right? So if we go ahead and, you know, do that, z squared minus 5, then when we do the derivative of this, usually we just write du equals the derivative, and then so this would be 2z dz. So you don't necessarily have to write du dz every time and then, you know, bring it over and all that. So what we can see here is that it's not exactly what we have on the outside here. We actually have just z on the outside. So what we can do is just like we brought the dz to the other side, we can bring that 2 to the other side. Okay, so we can divide both sides by 2. There's no reason we can't do that for sure. So it's like 1/2 du equals z dz. Now, this expression right here would be the square root of u du times 1/2. And it's constant, so we can just bring it on the outside, right? So we subbed the z squared minus 5 with u. We subbed the z dz with 1/2 du, right? And we kind of move the pieces around at the same time, but they're all there. Okay, so this will often be the case where it's off by like a constant or something. If it's off by a whole variable, then you might not be able to do something like this. Okay, so this really only, it's really only going to work when it's a constant. So let's go ahead and evaluate this integral now. So this is u to the 1/2, of course. So it's going to be u to the 3/2 over 3/2. So I guess I'll just write it out first. So u to the 3/2 over 3/2 plus c. And then we can go ahead and simplify that a bit to 1/3 u to the 3/2 plus c. And then again, of course, we want this to be in terms of z, not u. So we'll go ahead and sub it back in here. And we'll get 1/3, what was it? Z squared minus 5 to the 3/2 plus c. So we end up with an answer. So if we start with z, we want our answer to end up having z as well.